In this video, we will intuitively explore the concept of curl. This mathematical tool is essential across multiple fields. Curl is one of the coolest and most important mathematical concepts. It represents the tendency of energy to rotate around a point. In this video, we'll establish a graphical link between the rotational nature of curl and its analytical calculation, as well as its formula in 2 and 3 dimensions. The symbol for curl can be written either as curl or using the Nabla operator followed by the cross product symbol. In 3 dimensions, curl is expressed as shown here. Notice that the input to this vector will also be a vector with 3 components, since we are working in 3-dimensional space. Each component of the input vector is indexed: I for the x-axis, j for the y-axis, and k for the z-axis. The output is a vector with 3 components, where each component describes the rotation around a specific axis. For example, the first component describes rotation around the x-axis, i.e., in the yz plane. The second describes rotation around the y-axis, i.e., in the xz plane. The third describes rotation around the z-axis, i.e., in the xy plane. To fully understand curl in 3 dimensions, we'll start by explaining it in 2 dimensions. Here, the input vector lies in a 2-dimensional space. Each component depends on 2 variables. The result in this case is a function describing the rotational behavior of field lines in a plane. For our case, this plane is the xy plane. At each point, the value of the curl can be positive, indicating a counterclockwise rotation, 0 indicating no rotation, negative indicating a clockwise rotation. Let's analyze the case of a positive value. Consider a point M in the xy plane. Suppose this point is the origin of an orthonormal coordinate system. Let's take the case of a field that rotates clockwise, projecting the forces onto the x and y axes. On the y-axis, the projected forces behave as follows. To the right of point M, the force is positive and increases from 0 to a maximum before returning to 0. To the left, the force is negative, decreasing from 0 to a maximum negative value, and then returning to 0. Similarly, for forces projected onto the x-axis, above point M, the force is negative. Below, it is positive, evaluating the partial derivatives of the components. The derivative of the y component with respect to x increases linearly, resulting in a positive value. The derivative of the x component with respect to y decreases linearly, giving a negative value. Thus, the difference, positive-negative, yields a positive curl. From this, we deduce that counterclockwise rotation corresponds to a positive curl. Clockwise rotation corresponds to a negative curl. No rotation corresponds to 0 curl. For example, consider field lines in 2 dimensions. A clockwise field results in a negative curl. A counterclockwise field gives a positive curl. A field with no rotation has a curl of 0. Moving to 3 dimensions, the curl formula comprises 3 components. One in the yz plane, another in the zx plane, the third in the xy plane. Essentially, the curl in 3 dimensions is equivalent to combining 3 2-dimensional curls. One in the jk plane, one in the ik plane, one in the ij plane. For a better understanding, let's consider the following example. We can evaluate the curl of a vector proportionally to its intensity. This example of proportional scaling helps us intuitively understand the concept, even though it doesn't correspond to actual physical values. The intensity of rotation can be represented as follows. A weak counterclockwise rotation in the jk plane might be assigned a value of +1 in the vector. A slightly stronger clockwise rotation in the ik plane might be assigned a value of -2. A much stronger counterclockwise rotation in the ij plane could be represented by a value of +7. These values are purely illustrative and are meant to explain the concept of scaling the intensity of rotation. They are not intended to represent real-world measurements or exact calculations. I hope this video is helpful. Thank you for your attention. Please subscribe. This motivates me to continue.